Welcome to Chapter 4 on forecasting. Now, unfortunately, businesses don't have a crystal ball. However, when they prepare their budget, they need to be able to forecast numbers and come up with an estimation of what they expect to have for costs and revenue in the future. What we're going to look at in this chapter is a variety of different techniques that a business can use to forecast the numbers that they will need for inclusion within their budget. Forecasting will focus on the cost behaviour and budgeting sections of the syllabus, and it's likely that you will see questions on forecasting tested in section A of the exam. There's a number of techniques that we're going to look at in this chapter, and if we flip over onto the summary page, we'll briefly discuss each of those techniques.
You can see from the overview diagram that we've got a lot of techniques to cover. So if we're looking at predicting our costs, we're going to be using the high-low method as a way of splitting the costs into fixed and variable elements, using scatter graphs and also linear regression calculations. And we'll be looking at the reliability of those calculations through R and R squared, so correlation coefficient and coefficient of determination. We'll be looking at two other techniques as well. We'll be looking at time series analysis, and there are two approaches to that, using the additive model and the multiplicative model. And then finally, we'll be looking at using index numbers to predict future costs. Let's start off by thinking about why it's important for businesses to be able to predict costs at different levels. Well, if they're going to plan and make decisions, they need to know what the likely costs are if they make a certain number of units. Therefore, if we can identify the relationship, so work out how much it's expected to cost us at a given output level, then we can use it to try and use some what-if analysis and think about whether or not it's a good idea to increase production levels. If there is a relationship, then we say there's correlation. So that's a bit of terminology there. It's not just costs and the number of units that are produced. There may be correlation between other variables. So the taller you are, the heavier you are, and the further you're going, then the longer the distance, the longer the time it takes to make that journey. However, if we're looking at a journey, if you are flying for 2 hours, or if you're flying for 12 hours, there are still going to be some elements which will be the same, or the hanging around or the check-in at the airport. And it's the same really for costs. There can be an element of fixed costs and an element of variable costs. And that's why we need a model to predict how much of it is fixed and how much is variable. One of the ways of ascertaining the amount of correlation then is to draw a scatter graph. So you plot then all of the costs and all of the outputs on a graph. And you can see here from looking at this scatter graph that there is some relationship. The more the costs, the more the units produced, the higher the costs. Here then, costs are the dependent variable because they're said to depend upon output, which is the independent variable. So the one that's going up will be on the x-axis, the independent variable, and then the outcome that's observed, the dependent variable, will go on the y-axis. So we've got some correlation, and we can use our scatter graph to try and work out how much correlation there is and what a good estimate for the line would be, i.e. how much of the cost is fixed and how much of it is variable. The two techniques then that we can use for this are the high-low method, which is a simple approximation, and linear regression, which is a mathematical model to find the line of best fit. So let's have a look at popping some lines on. If we have a look then at the graph at the top of the page, we can see that the line here is y, so total costs are equal to a plus bx. And for costs then in chapter 3, we saw this as the total costs y are equal to the fixed cost a plus the variable cost per unit b times by the number of units produced, so times by the output. So we need to remember this formula, y equals a plus bx. Linear regression then mathematically finds this value of the line of best fit, and the way that it does it, if we look at the diagram, is it draws a line through all of the points. And the way in which that line is plotted is by taking the distance between the line and the points and squaring it, and it's the sum of least squares, or the line of best fit. In the exam then, if you're asked to work out the line of best fit, you need to use the formula for B and A. We've put them in the order B and A first because you need to work out B before you can work out A. Now those formulae don't look very nice, I know, but the good news is that you don't need to learn them because they're given to you in the exam. What you do need to know though is what all of the symbols and letters mean, and we'll see that in an example. But just to have a quick look, first of all, n is the number of pairs of observations. This Greek symbol here is sigma, and that represents the total. So sigma xy is the total of the x column multiplied by the y column, and we'll see those columns in a moment. Here we've got the total of the x column times by the total of the y column, and all of that is being taken away from the total of the xy column multiplied by n. And we're dividing that by the number of pairs of observations times by the total of the x squared column minus the total of the x column squared. It's really important when you're applying to these formulas that you remember the order of the calculations, so the mathematical rules. And the way that you might remember that is BODMAS. So you do what's in the brackets first, then you do the to the power ofs, then you do your dividing, multiplying, and then addition and subtraction. Remember on My Study then that in the resources that you've got available are some basic maths if you need a little bit more help with this. Once you've worked out B, you can pop it in to the equation for A. So we've got y bar, which is the average of all of the y values. So this means average minus bx bar. So we've got a value of b up there times by x bar, which is the average of all of the x's. And here we've just written out how you calculate the averages. So y bar is the total of the y column divided by the number of observations. And just a reminder down here then, you could use this to work out the line of best fit for any pairs of data. It doesn't just have to be costs and output, but that's primarily what we're concerned with. What we're going to do now then is to have a go at applying these formulae to some numbers. So we've got some information here for Wigwam, the maker of these tents, and what we've got then are some past observations about how much it costs for the number of units that are produced. And what you'll see then is that those costs have been plotted on a scatter graph. So we can see that there's an increase in output, and that corresponds to an increase in costs on the y-axis. So we can see that there's an approximate linear relationship, but if we put a ruler on, we'll see that actually it's not a completely straight line. So what we need to do is calculate the regression line. So calculate y equals a plus bx, and then we're going to use that line in part B to estimate how much it should cost for 240 units and 700 units. So there's a practical application. In order to answer this then, we need to set up a table and we need to work out the values that are needed for the formula. So we need to set up the following table. So we've got X then, which is the number of units. So we're just going to copy that across, 280, and the costs there are 46,500. We're going to work in thousands to keep the numbers easier, so that'll be 46.5. And then we've got the XY column, which is X times by Y. So 280 times by 46.5 is 13,020. X squared, so 280 squared is 78,400. And then the Y squared column, which is something we will need again in a while, so we'll use that now, 46.5 squared, so that's 2,162.25. And remember, all of the ones with Y's in them are in thousands. And then we need to do the same for the other observations, 350, 200, 160 and 240. Once you've worked out what you're doing, this is effectively a number crunching exercise, so make sure then that you're happy with the calculations. Probably a good idea to complete the table and resume the recording once you've done that. So pause the recording, fill in the table and then resume. So once you've completed it, the table should look something like this. What you need to do now then is take those totals for each of the columns and put them into the formula. So B then, remember, was equal to N times by the total of the XY column minus the total of the X column times by the total of the Y column divided by N times by the total of the X squared column minus the total of the X column squared. So let's look at pulling the numbers in. N is equal to 5 because we've got 5 levels of production and the associated costs. So we've got 5 times by the total of the XY column, which is 53,345, minus the total of the X column, which is 1,230, times by the total of the Y column, which is 208.8. Divide that by N times by the total of the X squared column, 324,100, minus the total of the X column, 1,230 squared. Now that might look quite awful to put into your calculator, but you can do it in stages if you wish to. Just remember to do what's inside the brackets first. And the answer you should get is 0.092. But remember that that is in thousands. So B then is the gradient of the line. And what you're going to do now is to pop that into the equation for A. So A, remember, is the total of the X column divided by 5, so the average of the Y values, minus B, so 0.092, multiplied by the average of the X's, so 1,230 divided by 5. And that should give you 19.128, and that is in thousands as well. You may have got a slightly different answer if you'd used the unrounded number on your calculator as the value for B, but it would have been in the similar ballpark. So the equation then for the line is Y is equal to A, which is 19,128, plus 92x. So multiply both of those by 1,000 to give Y in dollars. We can now use this then for our predictions in part B. So in part B of the question, we have to predict what the costs will be, so predict Y, when we make 240 units. So when X is 240, so Y will be equal to 19,128 plus 92 times by 240. So Y is going to be equal to $41,208. What does this mean? Well, we're estimating that there are going to be fixed costs of $19,000 and variable costs of $92 per unit to give us our total prediction. What we can do now as well is we can also use it to predict what costs will be when output is 700 units. So by plugging the numbers into the formula, we can predict that our costs will be $83,528 if we produced 700 units. Now, how could this be tested? Because obviously there's quite a lot that we've done there. Well, you might have to work out the values of B and A, having been given their table completed. You might have to fill in parts of the table, or you might have to use an equation that you're given to work out the total costs. A final way that this could be tested is it could say which one is likely to be more accurate, your prediction for 240 or your prediction for 700 units in B2. If we look back at our table here, you can see that we have got experience of producing between 160 and 350 units. Therefore, 240 falls within that range and we can be fairly confident of our prediction. 700 though is beyond that range, and that's what we call an extrapolation, because we're making assumptions that costs will continue to be the same. It might not be the case, because doubling your output to 700 units from the current maximum may result in additional fixed costs being incurred, for example, additional rent. How useful our regression line is then is going to depend upon the correlation, which remember is the relationship between the two variables. And what we've got here then are some different graphs, and we need to think about the relationship between them. So this first one here then has got R equal to 0, and that indicates that there's no correlation whatsoever. There's just a complete jumble of plottings. There's also no correlation in the second diagram here. So the first one looks like a complete random assortment, but the second one may actually look like a line that we're familiar with. It's the line for fixed costs. Fixed costs are constant regardless of the level of output, so therefore there's no correlation between the number of units produced and the total fixed costs. The two that we have at the bottom then show first of all perfect negative correlation, where R is equal to -1 and we've got a downward sloping line, and perfect positive correlation where R is equal to +1 and we've got a line that slopes upwards. This second one here then, where R is equal to +1, could be the relationship between number of units on the x-axis and y-axis if the only thing driving cost is the number of units produced. An example then of negative correlation is as one thing goes up, the other thing goes down. So perhaps the more beers you have, the less able you are to walk in a straight line. Or more seriously, the fixed costs per unit fall the more units are produced. Rather than just relying on a diagram to work out the amount of correlation, we can actually use a mathematical formula. And here it is, given to you in the exam. Now this one might look even more hideous than B, but actually you'll notice that the top and this first bit on the left hand side are what we've already calculated for B. So we've only got an extra couple of things to do, couple of steps, and remember you can break down the calculation. So the first thing we need to do is look at the total of the y squared column times by the number of observations minus the total of the y column squared, and we need to multiply that by the bottom of the equation we already have, and then we need to square root the whole thing. And the great thing about the correlation coefficient is you can have a really good idea about whether or not you've got the answer right, because it has to be between -1 and 1. So if you get an answer of 16, you know it's incorrect. And questions can arise where you might just be tested on knowing what the correlation coefficient means, as well as actually having to calculate it. So let's have a look at a calculation now. So in example 2 then, we need to work out the value of R, the correlation coefficient, for the data that we've just seen in example 1, wigwam. So R then is equal to the number of pairs of observation times by the total of the XY column minus the total of the X column times by the total of the Y column. And we need to divide that by square root of 5 times by the total of the X squared column minus the total of the X column squared, and then we need to multiply all of that by 5 times by the total of the Y squared column, which is 8,924.20, minus the total of the Y column squared. And that is a lot to put in one go, so you may want to break it down. You may already have broken it down. We've got 9,901 on the top, and then we've got 107,600 times by 1,200, so 1,023.56. We can square root all of that before we divide. And remember, when you put all of that in and you press equals, you're looking for an answer between -1 and 1. And you should get, if you put it in correctly, 0.943. And it's very close to 1, so that indicates that there is strong positive correlation. And we'd expect that as the more wigwams are made, the cost rises. We can take that further and we can look at something called R squared. R squared then is the coefficient of determination, and this looks then at what proportion of the change in Y is explained by changes in X. So for example here, it's saying how much of the increase in costs Y is explained by the increase in the number of units X. The important thing, however, is it does not prove cause and effect. It just suggests that there's a link. And with something like cost and number of units, we're quite happy to say that it's making more units that causes the cost to rise. But with some things, it's harder to know, even if there's a link, whether or not which one is the driver, which one is causing it. The value for the correlation coefficient had to be between -1 and 1, so therefore the coefficient of determination, which is just R squared, has to be between 0 and 1, because if you square a minus it becomes positive. So in example 2 we calculated that R was equal to 0.94, so here we want to calculate R squared, so therefore R squared is equal to 0.94 squared, which is 0.8836. So what we're saying then is that this suggests that 88% of the increase in cost can be explained by the number of units being produced increasing. It means, however, that the other 12% is due to other factors. Example 1 walked you through all of the different stages. What we're going to move on to now then are 3 sort of types of questions that you might expect. So what you can see here then in example 4 is that all of the table, the number crunching has been done for us, and then there are 3 possible questions that could arise from that information. So what we're going to do now then is to work out first of all the value for B, the gradient, then the value for A, the intersect of the y-axis or the fixed costs, and finally the coefficient of correlation. And you might want to just amend this because actually it should say the correlation coefficient. So remember for B then we're looking for n times by the total of the xy column minus the total of the x column times by the total of the y column, divided by n times by the total of the x squared column minus the total of the x column squared. So n then is equal to 11. xy here is 13,467, and the total of the x column is 440, and the total of the y column is 330. Divide that by n times by the total of the x squared column, 17,986, minus the total of the x column squared, so 440 squared. So that equals 0.69. And that's going to be answer D. Make sure you don't pick answer C because that has a minus in front of it. Now we need to find the value of A, so we're going to need to use our answer for B there. So we're looking at the average of Y minus 0.69 times by the average of X. So the answer here then is 2.4. Got some nice straightforward numbers. Finally then we have to work out in C the correlation coefficient. So the value then for the correlation coefficient is found using the formula for R. So we're looking at the total of the xy column times by 11 minus the 440 times by 330, the total of the x column times by the total of the y column, and divide that by this massive square root. So 11 times by 17,986 minus 440 squared that we did above, and then we need to multiply that by 11 times by the total of the y squared column, which is 10,366, minus the total of the y column squared. And as before, you might want to break that down into stages, but you should get an answer equal to 0.63. So that's answer B. So you need to make sure then that you feel confident with the crunching of the numbers and putting them into your calculators here. As well as knowing about the technique, we could also be required to talk about advantages and disadvantages. So linear regression then gives us a definitive line of best fit that we can use for our predictions. And it uses all of the data, and we can get a fairly decent result with quite a small sample size. And especially in a dynamic business, we might not have been making the same thing over and over. Lots of processes will be linear, and so linear regression will work for them, so it will be possible to fit them to a straight line. However, we're making the assumption that there is always a linear relationship between X and Y, and for some things that might not be the case. Because we're including all of the data, there might be some that are atypical, which skew the results. We're also using the past to try and predict the future, and there may be changes that have not been built into this. Also, for regression analysis to be used, every observation should be independent, whereas in reality, it might be that 1 month or 1 period's experience affects another. We've also mentioned this idea then of extrapolation outside the range of observations that you have currently observed could have an impact on the cost patterns. So, for example, there may be a step to fixed cost. The next method that we are going to be looking at is something called time series analysis. A time series then is when we are looking at, again, using historical data to try and make a prediction. But we're making a prediction then which has another element to it than just a straight line. There are 4 different components to a time series. We've got the trend, which is the underlying pattern. So it could be represented by a regression line. It's usually a straight line or a smooth curve, and we will often find it using moving averages, but as I said, we could also find it using regression. Seasonal variation is when we have got a reoccurring pattern that kind of masks that trend a little bit, and it's very repetitive. It doesn't have to mean spring, summer and autumn and winter. It can be any regularly repeating pattern. So for example, it could be weekly or quarterly. We also have longer term variations for cyclical variations and random variations which are not predictable and due to rare occurrences. The ones that we're concerned with are the trend and the seasonal variations, because those are the ones that we can predict. So when we're looking at using time series for predictions, we're going to be concerned with trend and seasonal variations. And we'll have a look at the 2 models we've got, and then we'll see what this would look like on a graph. The first model that we're going to be looking at is the additive model, where all of the components are added together to give us the time series. But we can only use this if the components are independent. So a better model then is the multiplicative model, where all of the components are multiplied together. So the time series then is equal to the trend times the seasonal variation times the cyclical variation times the random variation. But in the exam, the good news is we only need to deal with the trend and the seasonal variation. We're going to calculate the trend using moving averages. And what we're going to do then is to take an average of all of the results to work out what the average would be. It's slightly different to an ordinary average, depending on the number of periods or the number of seasons, if you like, that we have in our situation. So if we've got a 5-day week, we'll use a 5-period moving average. If we're looking at quarters, we would use a 4-period moving average. So it's how often the pattern is going to be repeating. So if we have a look at it all on a graph, first glance then, if you just saw the solid line which was showing what had actually happened over the last 3 years, you might think that there wasn't much of a pattern. It seems to be very higgledy-piggledy. However, if you take a step back, you can see from the dotted line that we've got an underlying trend. So it's on the up and there is an underlying rising trend. You can also see that there is actually a bit of a repeating pattern here. So we've got then these spikes which appear every sort of in quarter 3 of each year, And we've also got a much smaller spike in quarter one. The idea being then is that if we know about the seasonal variation, so quarter one a little bit and quarter three a lot are above the trend line and 2 and 4 below it, we can start to use it for predictions. So if we wanted to predict what our results might be for 2004 quarter three, well, we could carry on the trend and then we could predict that it would be above the trend line because of the seasonal variation. So this is more useful then than just regression analysis if we do have some kind of fluctuations. And seasonal variations can apply to lots of different businesses. So toy retailers seeing a spike in the months before Christmas, or it could be newspaper sales also experiencing repeating patterns, more people buying newspapers at the weekend when they've perhaps got more leisure time than midweek. If businesses have an expectation of the level of demand, then that can help them to produce the right number of units accordingly. So how do we calculate these seasonal variations? Well, once we've got the trend from moving averages or regression, then we can calculate the seasonal variation using either the multiplicative model or the additive model. On the additive model, the seasonal variation is the actual observation, so the time series, what we've seen, less the trend, and that will tell you if it's below or above. And with the multiplicative model, we take the observations and divide them by the trend. In example 5 then, we're going to have a look at using some moving averages. So we've got the actual observations then in the first column, the time series, and what we want to do is use the additive model to work out a 3-period moving average. And then we'll be able to work out the seasonal variation in the final column. So we've got a 3-period moving average. So we need to take the first 3 observations and work out the average of those. So we've got a total then of 12 divided by 3. And our 3-period moving average is therefore 4. And that sits on this line here because it is in the middle of the 3 valuations. Then we take the next 3 figures, which are all 5, and so the average there is going to be 5. Then we take the next 3 values, so we've got 18, so the total. And we carry on dropping down 1 each time. So we've got 18 here divided by 3 is 6. And then the next one is going to give us an average of 7. An average of 8. And you carry on until you've run out of numbers to average. So here then we can see that we have the trend is increasing by 1 each time. What we need to do though is we need to have a look at our seasonal variations. So that's the time series, take away this trend that we've worked out here. So 5 take away 4 is 1, 5 take away 5 is 0, so it's spot on the trend. 5 take away 6 is minus 1. So what we can see then here is that the seasonal variation is going to be below the trend line because 5 would go below the 6 on the trend line. 8 less 7 is 1, and 8 take away 8 is 0, and then finally we've got minus 1 again. So we can see here that we've got a repeating pattern. In the first block it's above the trend, in the third it's on target with the trend, and finally it's below the trend. These are quite straightforward numbers to illustrate the point, but you could see how if you had much more data you could apply these calculations. Under the additive model here then we've just got a little note as a check that the sum of the seasonal variations must equal 0. And here then you can see that they are going to equal 0. And on the multiplicative model the sum of the seasonal variations must equal the number of periods for the seasonality. So for quarterly seasonal variation, the decimals would add up to 4. So in example 6, again we're using the additive model and all of the seasonal variations have been worked out, but it appears there's going to need to be some adjustments. So if we add up all of our seasonal variations, we get to a total of +2. So what we need to do then is we need to take off 2 from all of the variations, and to make it even we'll adjust each of them by a half. So my seasonal variation now for quarter 1 is going to be 5.5, and that's a +5.5. My seasonal variation for quarter 2 is going to be -3.5. My seasonal variation for quarter 3 is going to be +4.5, and finally for quarter 4 -6.5. And now if we add them all up, you can see that the total comes to 0. So we've made the adjustments to ensure that the seasonal variations total 0. The reason that it might not have totaled 0 in the first place is because of rounding, so we're just correcting for any rounding. Example 7 combines regression and time series. So the underlying trend then is equal to y equals 400 plus 20x. So we've got our regression equation. And what you can see then is that x is increasing by 1 for each quarter. So it's going up then by 20 each quarter to give us our sales. So we're expecting growth in sales of 20 per unit. What we need to do then is we need to work out what the underlying trend is so that we can apply the seasonal variations which have been given to us as percentages, so using the multiplicative model, to give our predictions. What we need to do first of all then is to work out which quarter number is going to be year 6, quarter 1. So what we've got then is we've already had 5 years of observations, and there are 4 quarters in each year. So we've already had 20 observations. So quarter 1 for year 6 is going to see that x is going to be 21. It'll be 22 for quarter 2, 23 for quarter 3, and 24 for quarter 4. So the underlying trend then for quarter 1 is 400 plus 20 times by 21. So the trend for quarter 1 is 820, and it's increasing by 20 each time. So it'll be 840 for quarter 2, 860 for quarter 3, and 880 for quarter 4. And then to get our forecast sales, we apply our seasonal variation. So the seasonal variation for quarter 1 is -5%. So it's 5% below the trend line. So therefore we multiply our 820 by 0.95 to give our prediction of 779. For quarter 2, our trend is 840 and our seasonal variation is +10%. So multiply it by 1.1 and we add 84 to give us a prediction of 924. For quarter 3, it's +20%, so we're going to multiply by 1.2. So our prediction is 1032. And finally, for quarter 4, it is 75% below, so that's 25% below, so that's 75% of the trend. So that's a prediction of 660. So that is an example then of a section A question that could combine both linear regression and time series analysis and get you to work out a prediction. And it would be most likely to ask for your prediction for one of the quarters. But by doing all four, we get a bit more practice in. In example 8, we've got budgeted fixed overheads of 120,000 for the year with some seasonal variation. What we want to do then is to work out what the overhead should be for each quarter. So we know the annual total, but we need to split it out amongst the quarters. And rather than just doing 120,000 divided by 4 and saying that the overheads are 30,000 per quarter, there's some fluctuations. So it might be that if our overheads relate to things like electricity and gas, that there are extra heat costs in the winter, so it'll be higher in some of the quarters. Or maybe it'll be higher when production levels are higher. So what we need to do is apply the seasonal variations for each of the quarters. So for quarter 1, it's going to be 10% above. So again, using the multiplicative model, that will be multiplied by 1.1. So that will give us 33,000 in our budget. For quarter 2, it's 20% below. So we need to multiply it by 0.8. So that will give us a prediction of 24,000. For quarter 3, we're 15% higher, so we'll multiply by 1.15, which gives us 34,500. And finally, quarter 4 is just 5% below, so that's going to be multiplied by 0.95. So that's 28,500. Add all of that up then, and you'll see that you come back to your 120,000. It's just a way of allocating it during the different quarters, recognising the fluctuations in the overhead costs. Now, these forecasting tools might be the best way we've got of predicting future costs, but we still need to recognise that they are subject to error. The further into the future we forecast, the more unreliable it is, because the more we're likely to be subject to external changes, things that we hadn't known about. And that applies to lots of things really, not just to predicting costs. The weather forecasters are often quite accurate in the short-term forecast, but they might find it difficult at Christmas to predict what sort of weather we're going to have in the summer. Less data makes the forecast less reliable because any atypical or anomalies are going to skew the data more because they're going to have a greater impact. So having more data makes it more accurate. Just because something happened in the past, it doesn't mean that it will definitely continue into the future. And even if we are able to do a good calculation with regards to the trend and the time series, there might be a random variation, something that we just couldn't have predicted, which is going to upset the results. The final forecasting technique we're going to be looking at now is index numbers. An index number then measures changes over time for a group of items or an individual item. So one of the most common groups of items then is the Consumer Price Index, which looks at measuring inflation based upon a basket of goods. We get a feel for how the time series is changing by plotting a trend line. Another way then is to work out index numbers. And the index numbers are easier to see the underlying trend because the first year or the first period, the index will be equal to 100. So if in a subsequent period the value of the index is 102, it's very easy to see that there's been a 2% increase. Much easier than it would be if you have the raw data, especially if it's a very wide basket of goods. So you start off with your base year and then you work out the actual figure. You turn it into an index for each subsequent period. And you use this formula by taking the current period's figure, dividing it by the actual figure for the base year and timesing it by 100. A useful check is that if your price in, say, year 5 is greater than year 1, the number that you work out on your index has got to be bigger than 100. If all of the items in my index have an equal weighting, what we need to do then is to look at the combination of the beer, the pizza and the chocolate to work out what the cost of living index should be for X2 if X1 is going to be the base year. So if we add up then the total of the costs for both of the years, we end up with $6.05 in X1 and $6.25 in X2. To work out the price index then for X2, we take the actual figure in year 2 divided by the actual figure in year 1 and then multiply that by 100 to give us the index number. And that's going to give us an index of 103.3. What that translates to meaning then is that prices have increased by 3.3% for year 1 to year 2. And that's obviously an average increase because some of the goods may have increased more than others. The RPI then is a cost of living index in the UK that looks at the changes in costs of items of expenditure in the UK, and it looks at an average household. And the way that it looks at the cost for an average household is to take a basket of goods for looking at the prices. It's a huge amount of items, and obviously not every household will buy all of them, but it aims to weight them according to their relative importance, and the data is taken from a very wide range of sources. One of the issues though with index numbers is deciding what to put in the basket of goods and what weighting to give it. You start with a base year, so in the UK the RPI started in 1987, and you look at the comparisons are made since then. As I mentioned, then you need weighting so that different items are given more importance than others. We can also use index numbers to deflate our costs and put them all back into one particular year for comparison. So if you hear about figures where inflation has been removed to do a comparison, you'll still be able to see what we call some real growth. So our salaries might be very different to our parents. One of the reasons is due to inflation, but even if you strip that out, you can see real growth. There are other types of indexes as well that you can see in chapter 14 of your study text. So remember, in our forecasting chapter, what we're trying to do is to predict our future costs for budgeting purposes, and we looked at some of the techniques for these. So correlation then exists when two variables are related. So the change in one variable is accompanied by a change in another variable. And the degree of correlation is measured by the correlation coefficient. The coefficient of determination tells us what proportion of one could be explained by another. It doesn't, remember, give us a definitive answer. So over time then, the ownership of TVs has gone up and stocks of fish in the North Sea have gone down. They're said to be correlated, but I think we can see really that just because something's correlated, that doesn't mean there's a cause and effect relationship. The way then that we can plot that is onto a scatter graph to show it visually, or we can do the calculations for linear regressions. Remember, we calculate A, the intersect of y-axis, and B, the slope of the line. Another technique that we saw was time series with the two types of model, the additive model and the multiplicative model. One of the ways to find the trend is to use moving averages. The other is to use linear regression. Finally, an index then was used as a measure to work out over time changes in the average value. That could be the average value in terms of price or quantity of an individual item or a group of items, and they'll all be related back to the base year. You need to also be aware that all of these forecasts are not without problems.